Okay, well, I'll pick up the next session of this, and I was given a little bit difficult topic of talking about the history of methanol to hydrogen, and then also about fuel cells, and I had 10 minutes. So either one of those in an hour would be difficult, but so I put together a few slides here. I cheated a little bit. I talked to the organizers, and they said, yeah, it's close enough. We'll go with it. So hopefully this will be helpful. I am not going to talk about how one converts methanol into hydrogen. That's going to be picked up in a moment here. Instead, I'm going to talk a little bit about hydrogen specifically, how we make it, how we move it, the challenges that we face there. And then I'll switch gears, and let's assume that you have hydrogen. What are you going to actually do with it to move a vessel? So it's a lot to cover in just a few minutes here, but that's what my goal is. My name is Dave Edlund. I'm a co-founder and CEO of Element 1. We're headquartered in Bend, Oregon. My co-founder, Robert Schluter, you'll hear from momentarily here, he has moved over to the E1 Marine side, and so he runs that organization, and he's going to tell you a little bit about how we actually convert methanol into hydrogen. Element 1 is a technology development company. It's 12 years old. We develop methanol to hydrogen generators, and then we license that technology to partners for commercialization. Personally, I've been working in this space for all of my professional career, 35 years. I've seen a lot, and it's reached the point where I think that every 10 years I'm seeing the same things again. So there's a lot out there. Some of it works, a lot of it doesn't. And at any point, I'm happy to enter into conversations with people about why this, why not that, et cetera. Okay, hydrogen, you've heard a lot about. You've heard it mentioned today. It's in the news. It's in print media. Hydrogen's the most abundant element in the universe. I think pretty much everyone knows that. It's in water. It's in your body. Hydrogen itself is a gas. It's the lightest element, and it has a very, very low boiling point. Just a few degrees above absolute zero, in fact, which means that liquefying hydrogen is extremely difficult. Now, extremely difficult are two words that engineers use to mean expensive. It can be done, it is done, but it's expensive. So most of the time, you're going to find hydrogen being moved around as a compressed gas under very high pressure. Hydrogen is made from a wide range of pathways. And all of the pathways I'm going to mention here have been known for decades, easily 100 years. So you have reacting water with any carbon-containing material, coal, tires, hydrocarbons, et cetera. You can react oxygen or water with any hydrocarbon, and that's by and large what is done in oil refineries and petrochemical industry. You can electrolyze water. That means you take electricity to split water into hydrogen and oxygen. And finally, hydrogen is produced in very large quantities as a byproduct of certain chemical production pathways, particularly making olefins, which you can think of as precursors to plastics. So making hydrogen is not hard. Moving hydrogen is very challenging. Another code word for expensive. In these two photographs, you see two Class 8 commercial trucks. These are the largest trucks for moving freight on U.S. highways that are licensed by the DOT. On the left, you see a tanker truck. You may have seen these at gas stations. All of the 160, maybe 165,000 gasoline stations in the United States use this type of truck transport, petroleum products, gasoline and diesel, for the last few miles of delivery. On the right, that photograph is what's called a tube trailer. That tube trailer stores compressed hydrogen at about 2,600 psi. Now, the gross vehicle weight of each of those trucks is 80,000 pounds. That tube trailer carries about 1,000 pounds of hydrogen. Now, if you were to make hydrogen from that tanker truck, and the tanker truck had methanol in it, you would make enough hydrogen to fill 21 of those tube trailers. So that speaks directly to why hydrogen is expensive to move. And in fact, as that graph shows you, the purple line gives approximate cost per kilometer for moving compressed hydrogen in a tube trailer. And the number to remember, it's very easy to remember. It costs about $1 per kilogram of hydrogen to move it 100 kilometers. 100 kilometers, 60 miles. So if you start moving hydrogen 100 miles, a couple hundred miles, you're adding many dollars per kilogram to the cost of that hydrogen just by transport. So again, making hydrogen is easy, moving it is expensive. Water electrolysis is often thought of as the only way to make green hydrogen or low carbon intensity hydrogen. I actually like that term a lot, so I'm happy that that's been introduced. And it is, or it can be, very low carbon intensity. The problem or the drawbacks with water electrolysis are that it is an inefficient cycle. It requires a lot of water. Now, that may not be a problem here in Seattle, but there are a lot of places where water is not in abundant supply. And it requires an enormous amount of electricity, 50 kilowatt hours of electricity to make 1 kilogram of hydrogen. What does that mean for cost? Well, what do you pay for a kilowatt hour of electricity? If you pay 10 cents a kilowatt hour, you're lucky. That costs you $5 then just to make 1 kilogram of hydrogen. If you're going to move that hydrogen 300 kilometers, roughly 220 miles, add on another $3 for transport. You're already at $8 per kilogram just for the cost of getting that hydrogen to where you need it. The graphics in this slide illustrate the energy inefficiency of water electrolysis. If we're going to electrolyze water to make hydrogen and then use that hydrogen to make electricity, the best case is you're looking at roughly a 33 to 36% overall energy efficiency on that cycle. That means you're going to use 3 units of electricity to split the water into hydrogen, convert that hydrogen back to electricity in a fuel cell to get 1 unit of electricity. But fuel cells aren't the only thing we can do with hydrogen. And recently, there's been a flurry of announcements around hydrogen internal combustion engines. Now, burning hydrogen as a fuel is not a new idea at all. It's been around for decades. In fact, hydrogen is burned in rocket engines, right? As a side note here, it's been said that if it was not for the space industry and the need for liquid hydrogen as a fuel in rockets, there would be no liquid hydrogen industry at all, because it's simply so expensive to make liquid hydrogen. Cummins has recently announced a 15-liter hydrogen internal combustion engine, which they've started to book orders on, or book sales for. Caterpillar is coming out with a hydrogen internal combustion engine. JCB, which is a heavy equipment company based out of the UK with global operations, and many other engine manufacturers are all looking at internal combustion engines that will burn hydrogen. That is not an easy challenge to solve. BMW addressed this issue back around 2000 in their 7 Series automobile. One of the drawbacks to trying to burn hydrogen in a combustion engine is backfires, and also just the very low volumetric energy density of hydrogen. But if we compare both fuel cells and internal combustion engines burning hydrogen, there are pros and cons for each of them, and that's what I've tried to list here. On the positive side, fuel cells are quiet, they're very efficient, they have no emissions that are considered harmful. The only emission really is water. But on the negative side, they're expensive at this point in time. They require very high purity hydrogen. If we compare that to an engine is noisy. but it doesn't require as high a purity of hydrogen. Fuel cells work at very low hydrogen pressure, really a few pounds per square inch. Engines are going to use an injector, much like a diesel injector or a gasoline injector, to put the hydrogen into the cylinder or the intake manifold, and a somewhat higher pressure of hydrogen is needed to operate that injector. Really, I think the most compelling reason that engines are being considered at this point in time for hydrogen as a fuel is because engines are ubiquitous. It's a technology that is considered exceedingly mature. Manufacturing can be done virtually anywhere in the world, maintenance anywhere in the world. It's a known quantity. The challenge, the real challenge with the engine technology is that hydrogen injector. And that's just a very, very tough nut to crack. And it remains to be seen how successful this branch of the hydrogen energy technology is going to be as a commercial product. But it is something to be looking for. A little bit about emissions. So fuel cells are very clean, as I mentioned. Really, water is the only emission that you get from that. Now, water is a greenhouse gas. It's not one that anyone worries about. And there's really no reason to think that water emissions are harmful at all. When you burn hydrogen, you get nitrogen oxide emissions. Now, some nitrogen oxides are very, very strong greenhouse gas emissions. They also contribute to photochemical smog. And it's likely that some sort of exhaust treatment will be required to reduce nitrogen oxide emissions on hydrogen combustion engines. When we convert methanol to hydrogen, and again, that's going to be taken up momentarily here, but there are emissions from that. They're very, very low, but there are emissions nonetheless. What we do not have as far as emissions when we convert methanol to hydrogen are particulate matter. There's absolutely none. Nitrogen oxides, 0. Sulfur oxides, 0. Carbon monoxide, very, very close to 0. So our emissions are limited to CO2. And without going into a very lengthy sidebar about that, if you look at a complete well-to-wake cycle and you consider using renewable methanol, the CO2 emissions can easily be negative and almost certainly extremely low, even compared to the current US and European standards for greenhouse gas emissions. And that brings me to the end. Thank you.